Okay, so now we're in nuclear physics land. Now we're starting to talk about nuclear chemistry, the nuclear reaction, and this will help us understand a nuclear power plant. Um, this is apes. Welcome to college, kids. This is starting to get to some more nitty gritty stuff. Okay, so first there's this pattern that you see through the periodic table where the smaller elements, the stuff at the top, tends to have equal number of protons and neutrons. The mass is double the atomic number. So if you've got 4 protons, you're going to have 4 neutrons, and your nucleus would weigh 8. Okay. But as elements get bigger and bigger toward the bottom of the periodic table, that's a much more massive nucleus. So there's more little places where you can hold extra cargo. So if you'd like a metaphor, you can imagine that bigger cars tend to have more junk in them because there's more space for junk. So as our elements get bigger, the number of neutrons becomes bigger than the number of protons. You could probably ignore this, but if you're curious about chemistry, that's why the atomic mass grows so quickly for the bigger elements. The number of protons always goes up by 1 because that's what makes each element unique. But as you get to the bigger elements, they tend to have more extra baggage, more random neutrons included. And this really starts to matter with uranium. We're going to get to uranium. If nuclear physics is about mapping and knowing the forces inside the atomic nucleus, well, uranium starts to get really interesting because that's as big as you can get. Anything bigger than uranium on our planet just falls apart. It's too many forces. It's like when you have a car with all that crap strapped on top and like stuff on the bumper and stuff lashed to the hood and stuff sticking out the windows. And at some point you're just like, dude, that looks really sketchy. You've seen those trucks that drive junk down to junkyards and stuff, and they'll be like big, tall, super stacked cages on top of a little tiny truck. Okay, so the bigger elements are like that. They're unstable. On our planet, there's actually some elements that can't hold together at all. We call those the synthetic, artificial, man-made elements. Those are in pink here, and we make them in a lab. We just make them for a split second. If you make it, you get to name it. So like Lawrence Livermore Laboratory does a lot of fancy nuclear physics. And so they built a nucleus which only lasted for like 1/1000th of a second. But by measuring forces, they could tell that it was all stuck together. So they got to name that. They said Livermorium is an element with this many parts. And we know it's possible because we made it. It's just a dorky activity. To be honest, this is something that nuclear physicists do for bragging rights. So there's a Berkeleyium, there's a Californium, there's a Americium because America. And the process of making synthetic elements is just an exercise in seeing which forces are possible. So when you get into nuclear physics, you'll make these huge diagrams that have all these arrows that show you, well, these arrows all cancel out and pow, you could make this. And then you start throwing a bunch of stuff together and you get to make that nucleus and you get to name it. But like I said, on our planet, you can only get so big. You see, we have background energy. It's kind of warm here. So on our planet, you can only get so big. You can only get as big as uranium. You'll notice uranium is in red at the bottom of the screen there. And that's as big as you can possibly make something. Uranium's a big whoop. For the next 2 days, we're going to talk about uranium. We're going to talk a lot about uranium. Uranium on Earth is mostly one isotope. It's called 238. Uranium-238 is the majority of uranium. Almost all the uranium on our planet is 238. So if you were to grab a rock of uranium, that's an element, so it occurs in minerals, you just grab it, boom, so got a rock of it. And then you start to pick through every single atom. Those atoms would have 238 atomic mass units. So 92 protons and whatever, 146 neutrons. Okay, 238 is the most common isotope of uranium. Okay, and you have to know that, by the way. 235, that's interesting. You'll see later why that's interesting. And some things that you should know about uranium is that it's almost all 238 on our planet. There's a little tiny bit of 235 in there. The 235 is interesting. You should know that uranium is barely stable, so it's radioactive. It eventually falls apart. Pieces come off it. And that's what radioactivity is. So I'd like to introduce that vocabulary term. Radioactivity is the process of an atom falling apart. Pieces fall off. Uranium has a reliable decay process, radioactive decay. So uranium will dependably split by losing this part and then by losing that part. There are average decay products of uranium. Okay, so all the uranium on our planet is falling apart. It's decaying. You can tell how old the planet is by how much uranium is left. Fun fact, we have a whole lot of uranium in bedrock underneath Carpinteria, Summerlin, Montecito, and Santa Barbara. So the decay of that element leads to a radioactive gas that's very dangerous that many of us have in our homes because of where we live. We'll come back to that at the end of the school year. So uranium is barely stable, occurs on Earth in those three isotopes that are on your screen now. Almost all of the Earth's uranium is the 238. There's a little bit of 235 and a teeny little bit of 234. You'll notice that 236 and 237 are missing. We'll come back to that. Here's what's interesting about uranium. The guy who figured this out was a big whoop. Some guy was looking at this. He's like, yeah, the forces seem to kind of be stable for a little while. Average stability means that this would last like billions of years and this would last millions of years. The guy said, wait a minute, when you draw this, 236 isn't possible. In 236, all the arrows line up like this and that atom doesn't work. This guy was a big deal. This guy got a job working for the US government during World War II. This guy said, wait a minute, I have a theory. He said, when I was doing my PhD work, I had to draw a whole bunch of nuclei, and for this nucleus, 236, the forces oppose each other, and it looks like that nucleus would split. He said, what's weird about uranium is it's just barely stable. But if we could get 235 and make it into 236, take a U-235 and make it a little heavier. So he said if we could find the 235 uraniums and throw a neutron into there, that becomes 236, and that's not possible. This guy had a theory. He said if 236 is inherently unstable, we could make something that will fall apart. You could throw parts at an atom and make a nucleus split. You could split an atom by finding one, which is right on the edge of what's possible. and making it into one of the ones that is impossible on Earth. Nuclear physics is studying all of those forces inside the nucleus, and this guy thought, well, maybe there's a way to take 235, destabilize it by making it into 236. Then it would explode. And that would give off a lot of energy. He started to do the thing on paper, and he's like, well, if you take all those forces and you divide that into two little nuclei, there's going to be a lot of forces left over, you know, transformation of energy. Some is neither made nor lost. It just changes form. And he goes, wait, that's a lot of heat. The guy basically spent like 1.5 years doing the math, and he's like, the amount of heat, you know, draw it all on the whiteboard. He's like, the amount of heat doesn't make any sense, right? And he went to talk to all these other nuclear physicists, and he's like, you guys, look at the amount of heat you get for U-236 splitting. And everybody's like, yeah, checks out. And this was at the heart of the American nuclear weapons program, and that also led to the nuclear energy program. Now you understand why uranium is special. So first we're going to do a little bit of uranium mining, and then we're going to build a nuclear reactor, and then you're going to understand the reaction that gives off the heat, and then you're going to see how that heat is used to make electricity. We just went from high school level to college level to nuclear power. And I hope you have questions for me, because I can't imagine this is easy for you, and I know it's intimidating for a lot of you, but you'll have to be able to do this. So I'm here to help.